switch on the video recording. Thank you, Gianfranco. I would like to share some slides initially, just to introduce Gino. Where is it? Oops, sorry. Here it is. Okay. Okay, so let's stop with the cassella and go back to our conference. So I hope everybody is connected again. I would like to introduce the third keynote speech of DRCN 2021 by Gino Masini. And Gino is a principal researcher and standardization manager at Ericsson in Sweden. And also he is the chairman of the working group number 3 dedicated to RAN in 3GPP. He has more than 20 years of experience in telecommunication, receives his electronic engineering degree from Politecnico di Milano in 1996. Actually, as a personal note, Gino and I were in the same course, so we graduated the same year. And then he received the MBA from Bocconi School of Management in Milano in 2008. He has been a researcher at the Department of Electronics at Politecnico di Milano and worked for a European Space Agency and the Italian Space Agency in that period. Then he joined Ericsson, starting working with microwave radio links. And then since 2009, dealing with 4G and 5G radio access network architectures. It has been active in standardization since 2001, attending also ETSI, ITU, CEPT, and other standardization bodies, and then working in 3GPP, where he has finished his second term as chairman of the RAN Working Group 3. He holds more than, he authored more than 50 patents, most of which standard essential, and has several scientific publications. He holds a 6 Sigma certification, and he also co-authored a book on 5G radio access networks. So I would like to introduce the keynote speech by Gino today. The title is Janus Bifrons and the Matryoshka Radio Access Network Architectures for 5G. A very catchy title, let's say, and let's discover the meaning. So the 5G radio access networks, also known as RAN, specified by 3GPP, has been a result of efforts by all stakeholders in order to support ultra-reliable low-latency communications, accommodate centralized, distributed, and monolithic developments, and support cloudification, allow separation of control plane and user plane, and also to foster cooperation and resource sharing with the existing LTE, so to allow migration strategies, smooth migration strategies, let's say, from 4G to 5G. And this is why we can describe this architecture as Janus Bifrons and Matryoshka. The first is because it supports both non-standalone and standalone deployments, looking at both past and the future, therefore. The second, because the base station is split into its components, nested one inside the other, like Matryoshka. So the 5G RAN architecture is future-proof thanks to its flexibility and will allow the development of many verticals that we are talking about in this period. So I am stopped to share my slides, and I give the podium, the virtual podium, to Gino. Thank you, Gino, please.
Thank you, Guido. I think you will have to make me a presenter if I am to share slides from where I am.
Sorry about that.
That's okay. First of all, thank you very much for your presentation. So there you go. Thank you. So now I can share my screen, and I guess if I do like this, you will be able to see the whole picture, right?
Yes.
Excellent.
Perfect.
All right. So this is a chance to look into the network plumbing, if you will. So up to now, I have listened to the distinguished speakers before me, and they have talked about network function virtualization and software-defined networking and cloud and many things. Well, actually, the radio access network architecture as standardized today for 5G by 3GPP is the plumbing that makes all of this possible. So we are going to take a quick look, if you will, behind the scenes, or exactly how, or under the hood, if you will, and see how all of that works. So first of all, it is a result of some scenarios and requirements for 5G, and this basically constituted a challenges for architecture back when 3GPP started studying and then standardizing this. And we are talking about a journey that started a few years back. I will also talk a little bit about the timeline, and all of this today is already in practice. We are in our third release into 5G, and this I will claim is a fairly stable and flexible basis for a lot of stuff and a lot of very fancy things that we are building on 5G networks. So then, what is 5G RAN? I will talk a bit about standalone, non-standalone, the choices we made for user plane and split architecture, and also some quick peek on the architecture and some 5G features. So first of all, the scenarios. Back in time when we started studying 5G RAN architecture, the scenarios were already quite diverse. I mean, we discussed everything from broadband experience to media, gaming, massive machine-type communications, remote-controlled machines, smart transport infrastructure, human-machine interactions, lots of stuff. Lots of stuff that required high throughput, high reliability, reduced or no latency, and service-based, certainly service-based architectures to go with it. Just an example, just on machine type communications, even this single use case has a wide range of applications. We go from massive MTC on the side of low cost, low energy, small data volumes and massive numbers. And on the opposite range, you have critical machine type communications, ultra reliable, very low latency, very high availability. So this 5G architecture would need to do, if you will, in a colloquial terms, everything and the kitchen sink. Also take a look at the requirements from the ITU. This is taken from IMT 2020, and you can check this in the ITUR report. So a peak data rate of in the tens of gigabit per second, user plane latency one way of as low as 1 millisecond, possibly even less if we're talking about URLLC, ultra reliable, low latency communications. 0 milliseconds for mobility interruption time. Up to 1 million devices per square kilometer. And to top it all off, you know, the icing on the cake, a battery life for 3GPP hypothesis that was 10 to 15 years for sensors in very hard to reach places. So again, 5G had to be, I would say, almost everything to almost everybody. So then how do we go about building an architecture for that? Well, we need to support enhanced mobile broadband. This is more of the same, but better and faster as opposed to 4G. URLLC had to be there. But then we also needed to make sure we had a single architecture, because if you manage to have a single but flexible architecture. You ensure that everybody in the industry stays in the same picture, they stay on the same page, and you have the momentum for the whole industry to build something feasible and commercially viable and to move onwards together. A single architecture to accommodate a centralized, distributed, and monolithic deployments, supporting virtualization. The writing was already on the wall several years ago, so we had to support virtualization in all the architecture choices we made. We had to support the deployment of certain functions in the cloud. We need to have a fully separated control plane and user plane for a centralized unit if we had to, and if the deployment needed that sort of arrangement. Then operators put up very important requirements on the table. They did not want to throw away their existing 4G networks. So whatever we decided for 5G, 5G had to be deployed together with existing LTE networks. They had to cooperate, share resources, and hopefully deliver a better end user experience to the end users. So we achieved that thanks to a functionality called dual connectivity, where in a nutshell, you are connected at the same time to a 4G base station and a 5G base station, and both of them provide resources to the terminal, to the user equipment. And of course, they have to cooperate. They have to interoperate. They have to exchange information over a lingua franca of the network interface. At the time, the migration path from 5G to 4G was not very clear. So in the end, in order not to leave any use cases behind, it was decided to accommodate different migration strategies according to an operator's strategy or industrial choice according to the operator's requirements in a certain country. All of this increased the pressure and the challenge for all the working groups in 3GPP. And to add insult to injury, a huge time pressure, because we had to release what we call world-class specifications while accelerating the release process. So this brought us to release 5G in a fraction of the time that it took 3GPP to release specifications for 4G. This led us to 3 release drops. So we had basically 3 releases in one: an early drop, a regular drop, and a late drop for the same release, namely release 15, which came out 3 years ago or 2 years ago, and it was the first 3GPP release that supported 5G. So when I talk about 3GPP, this is what I mean. 3GPP has these 3 branches: a radio access network technical steering group, a core network and terminals technical steering group, and a service and system aspects technical steering group. Then each technical steering group is organized in several working groups. The working group that I chair is called RAN Working Group 3, and it's the group that handles radio access network architecture, interfaces, and protocols. So if you will, we are responsible of how the various elements of the radio access network talk to each other. If you will, it's the place where you have a pivot between the radio access network and the core network. So you get to see radio network aspects, you get to see service aspects, you also have to have some decent knowledge of the service aspects and the core network aspects. I think it's one of the most challenging but also interesting groups to be in. Otherwise, I wouldn't be chairman. Of course, I would say that, obviously. So now, in a nutshell, this is what the NG-RAN architecture is all about. So on the left side, you have the Janus Bifrons aspect. Notice that you have the main building block are those blue cones on the bottom. They are called G node Bs and NGE node Bs. So a G node B is basically the building block for the 5G air interface, whereas the NGE node B is, well, you might say an LTE base station on steroids. It's an LTE base station to which we have taught a couple of new tricks, namely how to talk to the native 5G base station. Hence, this is an architecture that can connect happily, or hopefully, well, mostly happily, the 4G world and the 5G world, making them happily work all together. On the right side, you have the Matryoshka aspect. If you take the G node B, if you take the 5G base station, you can actually open it up. And we have opened it up into a central base, into a central unit, or G node B CU, and a distributed unit, or G node B DU, or actually several of them. Furthermore, we have had some fun in opening up the centralized unit to be able to separate the control plane from the user plane. So we have standardized the CUCP and the CUUP. And of course, we have also standardized all the interfaces linking together all these network elements. A word about deployment options. So we have the first important distinction between the two modes of operation. Both standalone and non-standalone deployments are possible. Again, for maximum flexibility for operators. We call standalone a 5G network connected to a 5G core network, providing service to 5G terminals. So this is up to now, or this was up to now, the normal mode of operation of any radio access technology specified by 3GPP. You had the 3G UTRAN network, and it was a standalone network. So you had the 3G core network, 3G radio access network, 3G terminals. Same thing as for LTE, and this is also possible for 5G. On top of the standalone, we also have the possibility of non-standalone deployments. Non-standalone deployments is where you have tight interoperation between G node Bs and enhanced 4G base stations. Now, to complicate things further, these modes of operation could connect, or in each of these modes of operation, the base station connect to the same core network. And this could be either the existing LTE core network for non-standalone operation, or the new 5G core network. Now, to complicate things a bit, you could also have non-standalone connected to the new 5G core network. And once again, as I already mentioned, this is to make sure all possible combinations by operators are supported in the standard, meaning operators did not want to be limited by a single deployment path or by a single evolution path. Now, what do these things have in common? As I said, it's called dual connectivity towards the terminal. In dual connectivity, you have a master node and a secondary node, MN and SN for short, which concurrently provide radio resources toward the user to provide a higher bit rate. What the terminal will see, it will see a master cell group and a secondary cell group. Of course, the master node is the node that actually gets to control the terminal in terms of radio resources usage. So the terminal still sees one node to which it responds to. Nonetheless, this master is in constant communication with the secondary node, making sure that all the resources are used in the best possible way. Combining the various alternatives for master, secondary node, and the core network types, you have the different deployment options, and they have numbers which may sound esoteric. They're for reference only. By now, many of these have been prioritized. Some of these haven't had the interest from the operators that operators might have thought years ago. Nonetheless, all options that I will present now are fully supported in the standard. And of course, moving from one to the other, you have different migration paths possible according to operator strategy. So the most important one, and the option that was first introduced in the time domain, if you will, so it was the first one to come out, was so-called ENDC, UTRAN NR dual connectivity, or also called option 3. So the 4G base station is connected to the 4G core network. It acts as a master node, and you have the new 5G base station, which will act as a secondary node onto it. So this was the first stepping stone towards 5G functionality. An operator has 4G core network, 4G radio access network, he will simply add the new 5G base stations to the existing 4G base stations, and they will happily talk to each other using an enhanced version of the existing network interfaces. So 4G base stations talk to each other using the X2 interface and the X2AP application protocol. Well, this protocol has been upgraded and has been extended to add the required functionality to make sure that an EN G node B or a G node B that can talk to a 4G base station can interact and can provide dual connectivity services. So this was the first stepping stone that we put out, and already today, quite many 5G deployments are using this deployment option. They are in non-standalone mode. Then we also have the so-called NR-EU trend dual connectivity, where you basically reverse the orders. This time you have the 5G core network, you have the 5G base station as master, and you have the 4G base station as secondary. Now this time the master, if you will, gets to pick the interface. So the equivalent in 5G of the X2 interface is called XN. So this time we had to teach the 4G base station new tricks. We had to teach the 4G base station how to talk XNAP, how to talk through the XN interface to the new guy. This was interesting for operators that decided to start deploying the 5G core network to offer 5G services immediately, and also to introduce the 5G RAN at the same time. But in this way, they wouldn't lose the coverage that they already enjoyed with the 5G, with the existing 4G network, because the two would talk to one another. This is also supported in the standard. Then you also have the so-called option 7. In this case, we have taught the eNode B yet another trick. We have taught the eNode B the trick of talking to the 5G core network. Some operators said, I would like to deploy only the 5G core network, but still I would like my 4G radio access network to provide the basic coverage and to be in charge of managing and of mastering, if you will, the UEs. I would still like the 5G base stations to act as secondaries. So this is possible with this option. There are also further options. The standalone operation is considered to be a deployment option. And by the way, you can also have dual connectivity natively within 5G. It's called NR-NRDC, where you would have the 5G base station as master and secondary. You can also have the simple option of connecting the 4G network, the 4G base station, to the 5G core. That's called option 5. So notice, with all of these options, many migration considerations were possible. And then migration choice and path would depend to several factors like operator strategy, which timing the operator has to introduce the various building blocks, which will ultimately depend on the business decision on when to deploy 5G core network and the distinctive new 5G features. One of them is network slicing, for example. It can also depend on the availability. It did also depend, actually, because all of this is in the past now. It depended on new frequencies for NR, on the existing network density, on the foreseen increase of end user traffic, on the availability of terminals with the right features, and so on. And some examples of paths that might have been followed by operators. Initial NR deployments using higher frequencies, for example, above 6 gigahertz. Then you would have a smaller coverage on NR than on LTE. Then it made sense to use ENDC or option 3. Then you would leverage LTE for coverage and NR for higher capacity in busy areas. Then you would fully leverage your existing investments. And then when you would deploy the 5G core network, you could have the standalone deployment option. You could have option 4. Then this is NR for coverage and LTE as booster. In that case, you would choose to have NR as basis for coverage. An alternative would be to use LTE as basis for coverage, but still using the 5G core network. In that case, you would have options 5 and 7. Again, all of this was not very clear, especially to operators which provide a good part of the input to 3GPP. So back when we started in 2016, studying the new 5G architecture, we had to make sure that everything was to be supported in the first release. So the way this worked in 3GPP is in a very, very challenging and unusual way. So normally 3GPP works in releases, which are collections of features which are self-consistent. So you have a release, and then you have a set of specifications for the various parts of the network. And then if you deploy a network which is, say, release 14 or 15, you know that all the features specified in that release will work and will be consistent across all parts of the network. For release 15, we had to adopt this thing that's shown in the picture. We had to adopt 3 drops: an early drop, a main drop, and a late drop. So the early drop consisted of ENDC, which was the most popular at the time. The main drop included the standalone mode, or the native 5G with 5G core functionality option. And the late drop included the remaining dual connectivity options, so NR and RDC options 4 and 7. This is how we obtained the full-fledged set of 5G architecture options and deployment options and functionality in the same release, but we could spread it out in order not to exceed the available resources at that time for our standardization meetings. Now, a little bit more into the details of the split architecture. Up to now, notice I have talked about the Janus Bifrons, if you will, element of NG-RAN architecture. How the NG-RAN architecture makes sure that it looks at 4G and native 5G, or past and present, or past and future, if you will, like the eponymous ancient Roman god, Janus Bifrons, two-faced. Now we'll look at the Matryoshka aspects. So Matryoshka is, of course, the well-known Russian dolls where you open it up, there's one inside the other. So up to 4G, or actually in 4G, it was a distinctive feature of the 4G architecture. The logical node, and by the way, a logical node is basically a set of logical functions, is basically an atom. It's an atomic node. You cannot split the 4G base station, the E node B, according to the 3GPP standard. So 3GPP standard doesn't look into it. If you want to do it, of course you can, but it's up to you as a network vendor, so it will be a proprietary feature. Now, with 5G, operators and vendors and all the stakeholders decided that it was time to specify a split architecture for the G node B. So G node B has been split into a central unit and one or more distributed units, like the Matryoshka. So you see the G node B on the right. We have a G node BCU, several G node BDUs within it, and of course, we have specified the interface connecting them, which is called the F1. It has its own application protocol, F1 AP, and it's fully specified by 3GPP. So this gives more deployment flexibility. It gives better support for all those low latency services, because now you can deploy your DUs closer and closer to the terminals, because then you can decide how much to centralize. I mean, you could, for example, virtualize the G node BCU. The G node BCU could be a collection of software instances of these functions running on a blade or running in the cloud somewhere. And the DU, you could decide to deploy it closer and closer to the network edge, in the network edge itself, as close as you want to your terminals. And that, of course, will give you better support for low latency services. In terms of multiplicity, you notice that one G node BCU may connect to multiple G node BDUs, and one DU may support one or more cells. So what we have done is we have concentrated over the radio frequency functionality into the G-Node BDU, and all the functionality which is needed to talk to the core network and to exchange information to other NGRAN nodes, we have collected it into the G-Node BCU. Notice that for the rest of the network, it's absolutely irrelevant whether the neighbor G-Node B or the XN peer, if you will, the node has no way of telling whether it's talking to a monolithic G-Node B, which is still possible, or to a split G-Node B, in which case it's actually talking to the G-Node BCU. So it's an architecture within an architecture, or a node within the node, if you will, hence the definition or the nice figure of Matryoshka. Now we were having fun, and actually we have decided to further split the G-Node BCU into its control plane and user plane parts for yet more deployment flexibility, because we realized that we could go ahead and collect all the user plane functions into a dedicated network node. Also in this case, this network node could be deployed as close as possible to the RAN or as close as possible to the core network. This could be fully virtualized. Also, in this case, you could have cloudification of these functions. So also in terms of multiplicity, this is reflected. So one CU-CP, which is the control plane part, may connect to a single CU-UP, but there may be several instances connecting to more than one node. And still one G-Node BDU may support one or more cells. So we have, as you've seen, we have opened up one more level, again, using a standardized interface. In this case, it's called the E1 interface, fully specified, and it's an open standard like all 3GPP standards. So it can be downloaded, analyzed, implemented, and it can be obtained free of charge as all 3GPP specifications from the 3GPP FTP servers. So it's fully specified and standardized. Another thing we did, and actually this goes back to the Janus bifronts, we did something to the user plane protocol. In this case, as soon as we started tackling the issue of how to bridge between 4G and 5G, we realized, well, what do we do to the user plane? 4G has its own user plane. Are we going to have a dedicated user plane protocol for 5G or not? Well, we decided to have a unified user plane. The same user plane protocol then is used across three different interfaces. The XN interface, which is the interface between NGRAN nodes or G-Node Bs, if you will, or the 5G base stations, which are connected to the same 5G core network. The same user plane protocol is also used over the X2 user interface when it is used between a 4G and a 5G base station for dual connectivity. And the same user plane protocol is also used within a split G-Node B or within a split 5G base station between the CU and the DU. Then the huge benefit you have is that you have a single interface, a single instance, all the way from the lowest possible level of the radio access network to another radio access network node. So a single instance all the way, in this case from the DU, to another NGRAN node. So a single hop, no intermediate terminations, with evident benefits in terms of, for example, latency, because we have removed all possible and unnecessary termination points. This was already present since the early drop, since release 15, and it's one of the distinctive features of the 3GPP radio access network function architecture. The way we split the G-Node B also has impacts and has helped shape other RAN functions. For example, the CU and the DU have now become part of the positioning services architecture. So the CU is the node that exchanges information with the positioning services in the core network. This happens when you want to pinpoint the exact location of a UE or a user equipment or a mobile terminal, for example, for emergency services. The DU then hosts the transmission and reception points for positioning related radio signals and measurements. And again, this is all standardized and interoperable. Another way this has shaped the network functionality is when we talk about 5G multicast broadcast services. This is actually being specified and discussed in 3GPP as we speak right now. The work item is ongoing. So the Keynote BCU acts as coordinator for multicast transmission across the connected Keynote BDUs. So in this way, there's no need for external coordination entities outside the radio access network. This is, for example, a notable difference with respect to 4G multicast broadcast. It was called MBMS. In MBMS, in order to coordinate the multicast transmission over the different nodes using the SFN or single frequency network, you needed an additional node. So this means additional complexity, because an additional node to be specified and interoperable means you need to specify, as in fully standardize, the application protocol and the interface. Well, all of that is not needed for 5G because that's taken care of by the existing interface, the F1 interface between CU and DU. Another example, a very popular feature, or a very, I don't know if I should say popular or hyped or sexy or whatever feature in 5G, but definitely very interesting, is that 5G can act as a self backhaul. So 5G can be the access network and its own transport network. The feature is called Integrated Access Backhaul, IAB. Now, the way IAB node is standardized, IAB node includes a Keynote BDU and a mobile termination part, the MT part. The MT part is basically a subset of a normal mobile terminal of a UE, a user equipment. So the IAB nodes DU connect to the CU of a donor node via a standardized F1 interface with some additional features of this interface which have been fully standardized. And this is carried over the air interface. So once again, once we have set our radio access network architecture, this has also been pervasive and has also helped shape many other cool and popular features in 5G. Actually, the split architecture was so popular that it even influenced 4G. So we have backported the split architecture to LTE. So now it is possible in these later releases, we are finalizing this feature right now in these months, it is possible to split the 4G base station into a central unit and a distributed unit. And we have also created a standardized interface called the W1. So it's now possible, in addition to that, to carve out the ENOB user plane functionality. And notice that now it's Janus Bifrons and Matryoshka actually coming together, because we have decided to reuse the same E1 interface, which is reused towards the Keynote BCU UP. So a 4G base station can actually talk to the user plane part of a 5G base station central unit. And in this case, it means you have the same user plane node. Again, it could be virtualized, it could be placed anywhere you want in the core network or in the cloud. You will have the benefit of being able to use the same user plane node for LTE and NR. What are the challenges related to this? Well, some LTE functions had no counterpart in NR, at least in the first releases. For example, NB-IoT, the narrowband Internet of Things functionality, or machine type communications, or the LTE style multicast broadcast, or vehicle to vehicle communications. They initially had no counterpart in early NR releases. Hence, these features in LTE are not supported in W1, in the W1 interface, because the W1 interface has been backported from the NR counterpart. So what we did, we took a snapshot of the stable features for F1, and we said, okay, this is going to be the basis for the LTE counterpart. In addition, and this actually relates to how the innards of the LTE base stations are built, The protocols between LTE network and terminals are optimized for a monolithic node and not modular. So it's not very easy to carve out the different logical functions between the CU and the DU if you are in the LTE worlds. So these are all the challenges that 3GPP, and specifically 3GPP RAN 3, my working group, has had and is still overcoming as we speak now. But still, this influence is also felt on the LTE world. By the way, we also analyzed different types of splits. So there was a study item. Initially, we had even 8 different options studied for standardization. So each option meant different sets of logical functions for the 2 nodes and a different logical interface between them. So each option would have resulted in a different incompatible set of matryoshkas. You wouldn't have been able to have matryoshkas from one option inside the matryoshka from the other one. And in the end, we selected what is seen in this picture as option 2. And this resulted in the current architecture among the different options. So we had to select one to preserve interoperability and the benefit of using a single set of features. An additional thing that we also investigated is whether it would be beneficial and possible to standardize yet another split. Let's call it a low layer split, because the standardized split architecture is a high layer split. As you notice, the option 2 involves terminating the radio resource control protocol, which is the language that the network uses to speak to the terminals. It resides in the G-Node B CU, so in the centralized unit. And all RF functions reside in the DU. Of course, the design choice was for this in order to be able to exploit what we call non-ideal backhaul. So the idea was, what if we concentrated low-layer physical layer functions in a so-called RU, or a radio unit, assuming an ideal backhaul to carry INQ samples, INQ data. So this would mean further opening up the inner matryoshka, so the inner G-Node BDU. We also analyzed that. We had a few options for that. They are shown in this picture right here. What happened in 3GPP is that, well, 3GPP could not actually converge on a single option. So this was not pursued in standards. You are, if you want, this is available, the outcome of the study is available in a technical report. It's shown there, TR38.816, and you see exactly what was considered and you see the conclusions. But in the end, it was not pursued for standardization. So the discussion has been taken up, and the discussion continues in other industry alliances. For example, ORAN. ORAN has been discussing this in this area, and they aim to produce standards based on a subset of 3GPP functionality. And of course, what are the challenges that such an endeavor includes? Well, feasibility and performance of a low layer split option, they strongly depend on front haul performance, on the performance of the transport interface, which you are going to use between the, let's call it the G-Node BDU and the RU, because then this also turned to the radio configuration. So how fast you want your radio interface to be towards terminals, that will highly impact the kind of requirements you put on your ideal, but actually not so ideal anymore, transport network. So these are some of the challenges that this action involves. A bit of perspective. So you have seen now the 5G RAN architecture, and this is where we base our work on. So if you take a look at the 3G architecture, the UTRAN architecture, actually it was a split architecture. You had the RNC, you had the Node B, you had the IUR and IUB interfaces. Then we went to 4G, the EUTRAN architecture, which was monolithic. So then the base station functionality was collapsed in the same in a single node, and the inners of that node were not specified in terms of logical nodes and architecture, but only in terms of logical functions. And then we have moved towards a 5G with a split architecture. So the question might be, okay, what do we do for 6G? Do we go back to a monolithic architecture? Do we keep the benefits of the 5G architecture? Do we make it even more flexible? Well, only time will tell. Right now, 6G RAN architecture is something for my friends in R&D to discuss, and I expect it to hit the standards in possibly 2 or 3 years' time. At that point, I will probably have moved on as RAN 3 chairman because my term ends in a couple of months, but it will be a fun discussion to participate in. So in conclusion, the NR or new radio interface tightly interoperates with existing LTE networks while capable of standalone operation. We have specified interfaces and protocols, and 3GPP has been the heart of that. They have facilitated the evolution of 4 to 5G, and they have facilitated the uptake of services offered by 5G, and that's the Janus Bifrons. And additional flexibility was and is critical to 5 use cases. And we have achieved that thanks to the concept of nodes within a node. And that is reflected in the Matryoshka concept. So a couple of acknowledgements. All this, I couldn't have possibly done all of this work by myself. So I've had great help in preparing all this material by the vice chairs of the RAN Working 3 group, Gao Yin from ZTE and Sasha Sirotkin from Intel. And you will have also some references if you're interested in going a bit deeper on some concepts. Thank you very much, ladies and gentlemen.
So thank you very much, Gino. So now the floor is open for questions from the audience. Let me see if I see some questions on the chat. Yeah, Dominic. Hi.
Thank you, Gino, for a very nice talk. What is your perspective on using unlicensed bands and on using NTN?
Right. These are two very hot topics. So unlicensed bands, we actually have the possibility of using them in 3GPP. We have such a thing called NRU, which builds on a similar feature we had for LTE, which was called LAA, LTE assisted, I forgot the acronym, but it was basically the same thing. So the way we have done this is basically we have introduced a certain tweaks and features in the interface protocols so that the NR or the 3GPP specified NR can be a good neighbor of the unlicensed networks. So it is possible to be deployed. It's actually something which is supported by the NG-RAN architecture, although it didn't really require any specific feature in the architecture itself. So we have added a couple of information elements here and there simply to signal for that, for example, so that the base stations can signal to one another what band they're using. And this is business as usual, because normally when you set up the XN interface, okay, I'm using channel X, you're using channel Y, great, I'll keep this in mind whenever I hand over terminals. It's a basic feature. As far as NTN is concerned, it's a very popular feature right now. I'm actually one of the NTN enthusiasts within 3GPP and within Ericsson, also thanks to my background. When I was working at Polytechnic, I was working with the European Space Agency, so I'm one of the guys kind of bridging the gap between the terrestrial guys and the satellite guys. What we are doing now is we are specifying NTN for this release, which is release 17. It's going to be out in Q1 next year. It's going to be based on what we call the transparent architecture, meaning the base station is on the ground and the satellite and the uplink station and all of that, they are seen as a transparent repeater. So all the radio functionality and basically the building block, the NG-RAN node, we see it on the ground. Everything else is an RF transparent repeater. So this is what we're basing our work on right now, and NTN will be part of release 17. Yes.
Thank you. Also, especially for your support here for NTN.
Well, I think we are actually bridging the gap, because back when we started, there was a lot of suspicion between the two industries, you know, and especially the terrestrial industry. They started, or actually we started because I'm part of it. We started by saying, okay, yeah, you guys do whatever you want as long as you don't eat our spectrum. And then, you know, starting to discuss things, it came out, okay, but this might actually be interesting because we are tying everything to the same architecture and the same lingua franca, so it benefits everybody. I mean, the market just gets bigger. So it takes a while, and that's what 3GPP and what good standardization is all about.
So I see another question from Lija, my colleague Lija, please.
Hello, thank you very much for your fantastic presentation. Regarding the separation of the control plane also in the CU, which are the actual advantages that we have with that? Because, of course, it will create a great complexity. And would it even be feasible, thinking of the implementation point of view, to separate even the control plane and user plane in different nodes?
Yes, of course. Well, I could, the smart answer, I could quote one of my mentors within Ericsson. She's retired now. And at some point, I mentioned to her, well, but this is actually complex, to which she replied, well, so of course it is. That's why you're here, my friend. So normally we don't shy away from complexity. The benefit is that user plane functions, unlike radio-related functions, they're easily virtualizable. So then the key thing is to understand and be able to separate which of these functions can be separated or pulled out of the physical base station, if you will, and which cannot be separated because they make sense to stay within the DU. So there are some parts certainly that need to stay within the DU because, for example, they will affect immediately which kind of radio resources I am going to give to a certain terminal, or which kind of let me say, which kind of SSBs or bandwidth parts that terminal has to be allocated with, and so on. But there are other parts, like, for example, subscription-related information, or which services or QoS classes this guy has been assigned. Those actually can make sense to be virtualized and to be pulled out and be deployed, for example, in the cloud, next to or within the machines that act as your edge router, for example. So all of this was discussed, and all of this is already standardized because the E1 AP protocol, so the E1 is the interface linking the control plane and the user plane part of the base station. That's already part of release 15. I think we put it out as part of one of the drops. So it's already there. And actually, Ericsson, but also other vendors have products that exploit that particular split. So yes, it is possible. And I'm happy to say it is possible to overcome.
I think
okay,
we can.
Thank you very much.
We can take a last question from Ying Wang.
Hello. Thanks for the fantastic presentation. Really enjoyed it. I have a question regarding the IoT. So like narrowband IoT or just IoT in the current doesn't really support like even a completely standalone infrastructure. What's your thought on that? Like using deploying massive IoT devices in a complete 5G network?
Okay, so I don't think that's entirely correct to say that IoT doesn't support standalone. IoT is actually in the process of, first of all, what are we talking about here? So IoT, there's the LTE flavor. And of course, if you're talking about LTE flavor, you have to deploy it on top of the LTE specifications. So then when IoT was specified for LTE, there was no such thing as LTE split. So we had to draw the line at some point. And at that point, both operators and vendors came together and said, okay, you know what? It doesn't make sense to support the IoT functionality in the W1 interface. So you can, if you want, go for a split LTE base station, but any IoT support for that will have to come out of proprietary features. So it will have to be implementation based, which is still fine, because what we have here, remember, these are not standards in the way, I don't want to insult anybody, but these are not the standards the way Microsoft or Apple intend them: embrace, extend, extinguish. Actually, one thing that is really distinctive about 3GPP standards is that if you deploy release 15, you have the guarantee that any network elements that are release 14 or 13 or 12 compliant, they will perfectly work. So we never break functionality. So then any additional functionality on top of this doesn't break the standardized feature. So then NB-IoT is of course supported. It's not supported in the split version of LTE in a standardized way. But if there's a vendor that supports this for you in implementation, that's fully okay and that's fully compliant. And by the way, we have now specified IoT features also for NR. So I think we have now the full set of features. Thank you.
Got it. Thank you so much.
So thank you very much, Gino. I just want to ask you if you would like your slides to be made available to the attendees.
Yes, that is fully okay, because all of these slides try to put a clearer perspective on what is out there, and all the references that you see there are mostly to 3GPP and ITU publications, which are freely downloadable. On top of that, you also have 2 books. One of them is the one I participated in writing, is the first one. And the second one, The Dark Side of 5G, which sounds right out of Star Wars, was actually edited by Sasha, who's my RAN 3 vice chairman. So they're all very good publications for you to peruse, and sure, feel free to make this available.
So that will be uploaded in the same web page where you find the proceedings. Okay, so thank you very much.
One thing, perhaps you might want to convert them to PDF and get rid of the 2 animations. That will make them a lot lighter.
Absolutely, yes, of course.
Thank you.
Okay, so now we have to move to the next session. So we are a little bit late, but it was for the sake of this very interesting discussion for this keynote speech. So I hand over the podium, the virtual podium, to Sebastian Troia, who will be the chairman of the next session.
Hi, everybody. I'm Sebastian. Thank you, Guido. I'm going to share for a moment the program of today. So we are at the session 5, wireless networks and security. We have 4 presentations. The first will be done by Brandon Fubert from INRIA, France. So I'm gonna ask in the meantime to Brandon to raise the hand. And in the meantime, I'm gonna share his presentation by video.
Hi, so am I supposed to share the video myself?
No, I'm gonna share it.
Okay, perfect, thank you.
Thank you.
Everyone, my name is Brandon. I'm a third-year PhD student at the INRIA Lille in the north of France, and I'm working with Nathalie Mitton. And today I'm going to present you our work on a lightweight network interface selection for A-level communications in multi-technologies wireless sensor networks. So as an introduction, we are considering the use of wireless sensor network as a tool to help farmers in the case of smart agriculture. And the goal of that is to have wireless stations that are going to be able to collect data about the weather and climate to prevent risk of frost, for example, or flood, and to help make better decisions, such as the use of water or the use of pesticides, for example. And in those stations, we're going to need wireless technology to communicate the information. And the things with radio access technologies is that there's a lot of it. There's different ones, but each one have different limitations, such as here Sigfox. Sigfox is a great technology because you can send messages at a very long range, at a very low power cost, but you can only have a maximum of 12 bytes per messages and a maximum of 140 messages per day. And as you can see on the map here, with the blue points that are the real base station, there is a limited worldwide coverage. And as I said, there's a lot of different technologies on the market, but there's always a trade-off to consider, such as the spectrum congestion, the financial cost, or the coverage, and so on. And all of that makes it really hard to find the best fitted technology for the use case you want to have. So the idea we wanted to explore in my PhD is why not use several arrays in a single wire sensor network? And thus this gave birth to what we call multi-technologies networks, where a single node is going to be able to have multiple technologies such as Wi-Fi and Sigfox and LoRa, and it will have the possibility to choose the best technology, the best route, and the best links it wants to use to communicate its data. So we have to consider the fact that in this kind of network, in the same pair of neighbors, you're going to have multiple links because there's multiple technologies. And we want to have multi-hop networks because if a node is isolated because it's too far away from a base station, it will have the possibility to relay its data to a neighbor. And we also want in this kind of network to be able to support several use cases, like we want to be able to have a node that's going to monitor data such as temperature and also record video, for example. So for this kind of network, we need a reliable RAT selection scheme. And there's a lot of tools in the literature to do a selection based on different criteria, but the one we find the best fitted for this task is called the multi-attribute decision-making method. And the idea of this kind of tool is that you're going to formalize the problem with a decision matrix, as you can see on the slide here, with three different sets. The sets of candidates A, so it's going to be the different technologies available. P, the set of attributes, so the things you're going to consider in a selection, such as the bitrate, the power consumption, and so on. And W, the weights of each attribute, so this is going to be a value that's going to be representative of the importance of each attribute in the selection. If you want to put an emphasis on the power consumption or the bitrate, for example. And in in MADM methods, you find a lot of different methods, but the one that is the best, the most used and the most studied is called TOPSIS, for Technique for Order Preference by Similarity to Ideal Solution. And TOPSIS is a little better than the other MADM methods because it allows to select the best candidate based not only on the similarity to an ideal best solution, but also on the farness from the worst solution. And this method takes decision matrix as input and outputs a list of the technologies of the candidates with ranks, and of course the one that is ranked 1 is the best one for the case we want. But TOPSIS is not perfect, and there's two problems we have to consider. In the case of using TOPSIS on WSN hardware, the calculations, the computations are a little complex because on the long run, like for 3-4 years of run, if you run TOPSIS several times per minute in the long run, it's going to be costly in energy. And there's also a second problem that is called the rank reversal, and it happens when you suppress a candidate from the ranking, even if it's not the best. Like you have your ranking, you suppress the worst candidate in your ranking, and you redo the calculations, and the ranking may be different, and that's not supposed to happen. And this is caused by the way TOPSIS normalizes the values. It's based on something called the Euclidean normalization, and it takes in account every values of the alternative, every value of the attribute to consider of every alternative to calculate the value normalized for your alternative that you're calculating. So of course, if you change the set of alternatives, you're going to change maybe the order at the end. And we run experiment to see if it was really a problem. And as you can see on the graph, you have the matrix order, the square matrix, and the rank reversal prevalence. So you can see that for a matrix of 10 to 10 in 60% of the runs, we're going to have a rank reversal. So it's quite a big problem. And considering the technology selection for well-sensor network is going to be troubleful, because you're going to have to maybe switch the technology without a real reason behind that, and it's going to be costly in time and energy. So what we wanted to have is a method based on TOPSIS, but quicker, with less complexity and without the problem, the issue of rank reversal. So we changed the normalization algorithm, which is now based on fixed bounds. So for normalizing your values, you just have to have fixed bound on each attribute that are given by the application layer. And you're going to divide your values with those bounds to get the normalized value. So it's a quick operation, and because the bounds are fixed for each attribute, it negates the issue of rank reversal. And thus, in turn, it allows to reduce the complexity of TOPSIS. As you can see, you have the first computation here, which is the original normalization algorithm, and now it's new. And because we have fixed bounds, we can change the computations that are further in the TOPSIS algorithm, and in time that saves up as much as 5 mn minus 2 operations, with mn the dimensions of the decision matrix. And so we wanted to see how good it performs against the classes TOPSIS. So we implemented that on PyCom 5P's nodes, which are nodes with 5 different technologies available, and we implemented that with MicroPython. And here you can see the TOPSIS results. So on the graph, the red line is the classic TOPSIS results, and the full line is the results of our lightweight TOPSIS. And we have thus a mean speed up of 40%, and in 80% of the run, the selection is the same as TOPSIS. And it saves up as much as 448 microjoules per TOPSIS run based on the 5Pi datasheet. So on the long run, it's quite a big quantity of power. So as recap, we chose to use the TOPSIS method for multi-criteria selection in wireless sensor network to do the selection of technologies in multi-technology network. And we changed the methods to use a custom normalization algorithm to make it quicker and without the rank reversal issue. And we evaluated that in experiments with PyCom 5Pis to see that yes, it's quicker and it's able to save energy. So the end goal of this work is to use that selection method to select not only technologies but also route for making a routing protocol in multi-technologies network. Thank you for your attention, and if you have any question, I'd be happy to answer.
Okay, so thank you, Brandon. We are open to questions now. Okay, I think I can break the ice. Just a curiosity, are you going to apply to implement this the autopsies in a real in the field? I mean, at the beginning you showed some use cases, and I was thinking it would be nice to work this in the field with this stuff in the field. So are you going to do this in your PhD? You have some projects with that does this?
Yes, actually, this is the end goal. My PhD is it's a collaboration with a company that is named Sencrop, and they are conceiving and selling the stations that I was talking about. So stations to measure the rain, the wind, and so on. And actually, we have done already a prototype of a multi-technologies routing network, and we want to test that in fields in the north of France to see the growth of potatoes. And we actually have planned to, well, the project is a collaboration with Sencrop, but also with the University of Stellenbosch in South Africa. And actually, I was supposed to go last April in Africa to test the prototype in the field, but because of the COVID crisis, I didn't have the chance to go there for as of now. I hope I can do it before the end of my PhD.
Okay, that's very nice.
Thank you.
Other questions from the audience? Maybe I have a second question. I'm not expert in this field, but I want to understand that your wireless sensor network is a kind of ad hoc network, no? But how do you manage the monitoring of data that you can acquire from your sensors? For instance, you were planning to go to Africa to install your prototype, but let's say that you come back to France and you want to monitor your stuff there. So how do you were facing also this aspect of the project?
Yes, we are. So the idea is that you have mainly two kinds of technologies. Either you have to deploy your own base stations, like for LoRa, for example. And in this case, we are going to deploy base stations, connect them to the internet, and then with the cloud, we will be able to see the data we collect. And if not, that means that we are exploiting the network of an operator, like with Sigfox or LTE-M or NB-IoT. And in this case, it's the operator that is going to manage the cloud and from which we're going to have our data back.
Okay, got it.
Sebastian, I think you can.
Yeah, I can move to the second. Okay, thank you, Brandon.
Thank you.
I'm gonna call now Ying Wang. And here.
Yes.
Okay, you are ready there?
Yeah.
I'm going to share the presentation.
All right. So hello everyone, thanks for attending our presentation. My name is Ying Wang and this is my colleague Adam. We're going to present our work, the AI-powered real-time channel awareness and 5G NR radio access network scheduling optimization. This work is done on the CCF5G experimental platform that shifts the simulation-driven research to a more system implementation prototyping with a complete 5G end-to-end system implemented. First, I would like to talk about the motivation about this work. Security has always been an essential part in any network. 5G and the previous generation of LTE are both vulnerable to jamming attacks, which creates interference to hinder the communication of legitimate users. The flexibility and the performance in 5G enhancement are great for vertical applications and customizations. However, it does increase the difficulty and the complexity of cybersecurity. If we look like the inside of the signal, so in this picture on the left, it shows the different aspects in both frequency and time domain of received NR signal. We notice that there is this blue donor-shaped signal here, and that's the new design in 5G only. It's called the core set. It carries the control information. It is designed with flexibility regarding time, frequency in each of the frame. The configuration of the core set is flexible in the single beam condition, and is even more flexible in the multiple beam condition shown on the right. And that's our first challenge for addressing the 5G jamming and interference vulnerability. Is 5G and the subsequent generations of wireless communications have introduced additional flexibility, virtualization. However, it raises up the challenge to system security assurance. So based on the experimental result, the core set is actually more vulnerable compared to the data channels regarding the jamming attack. So if you look at the figures here, it shows how the controlled jamming signal attacking the system performance, how the system looks like. So the blue part is the jamming for core set, and the orange part is the jamming to the data channel part. So with core set jamming, the throughput decreased significantly, and the error rate increased significantly as the power of the jamming signal increases. So another challenge is in the system resilience, how we can detect the jamming in parallel with the communication, how we can generate real-time correction to preserve the resilience and continue the communication in the system. This by doing this, it will increase the reliability of the system significantly, and that's very essential for communication types that requires high resilience, like applications in healthcare applications.
To address these challenges, we propose a two-part solution. First, we develop an autonomous machine learning scheme that analyzes physical channel environment metrics to detect various types of jamming and interference on a 5G signal. We then incorporate this jamming detection system into a channel awareness and RAN scheduling system comprised of a cycle of over-the-air data generation, machine learning model training, jamming detection and classification, and 5G network resource optimization. We designed this system to ensure 5G communication resilience in the presence of 5G control channel jamming or interference. In order to detect and accurately respond to control channel jamming conditions, we employ several processes. First, we generate various types and levels of jamming based on user-specified scenarios. This jamming signal is fed into our lab 5G network environment. Key performance indicators collected in real time by the 5G network while the 5G signal is being jammed are then used as training data for the jamming detection ML model. Based on the ML model's channel environment determination, 5G network parameters are automatically adjusted to maximize a KPI of interest. Because our 5G system collects a wide range of network performance data, the performance indicator or indicators can be chosen by the user. In our case, we focus on adjusting the modulation and coding scheme to maximize the level of data throughput.
For machine learning models, it's critical to select the proper independent variables and labeling the result for the dependent variables. This shows the detailed cross-layer selection of features based on the experimental result and also the functions of the features themselves. The raw JSON files are captured by the GNLB or by the UE, detailing the NR connections with the cross-layer parameters, the KPIs, that is sent to the local storage where the current instance of the collected data. This is also parsed to store in the table in the SQL database. The imported KPI, the important KPIs include the downlink channel, uplink channel throughput, the package error rate, MCS, signal noise ratio, CQI, and power headroom report. So additionally, the technology, the devices, and the jamming scenarios, these are the external tables that is linked to the KPI table, so that it can be used for labeling process. This flexible design of the labeling allows future reuse of the data. As a proof of concept, we use the MCS for performance optimization, and at the bottom part, it shows the temporal-based MCS learning module. On this part, the MCS as well as the temporal data that captured are used to determine that for different MCS, what will be the performance predicted in different scenarios, and so that the optimal one can be selected. And this shows the result of the jamming detection and the classification. So the figure on the left, the upper one, shows the ROC curves of each of the model and also the comparison of the area and the curve, the AUC values. And also the table on the bottom shows the precision, the recall, and the F1 scores. So considering all the parameters, the overall performance logistic regression model is being selected here. We also considered a deep learning model, but we didn't select it due to the volume of data it requires is large, and also the number of the parameters needs to be tuned, as well as the computation complexity it needs on the hosting environment. Another note is that the model can be adapted to use on different parts of the components in the network. It can be a GNLB, it can be a UE or IoT devices. So for IoT devices, the power and the memory are very sensitive. So a model requiring low power computational complexity is preferred here. Recently, MIT HAN Lab has published the tiny deep learning system that enables low computation complexity deep learning on the IoT devices. And we are working on to try this method in our system.
Based on the captured training data and the resulting ML model training, an optimal MCS determination can be made that maximizes data throughput. The graph on the left illustrates the accuracy with which the ML model is able to predict the optimum MCS level with the highest resulting data throughput. An R-squared value of 0.94 is observed for the throughput average. Our results indicate a 30 to 100% increase in throughput depending on the level of jamming present in the channel environment. As seen in the plot on the right, as jamming signal level increases, our optimal MCS model results in a higher level of throughput and higher percentage increase in expected throughput when compared with the 5G protocol. There are a few facets of future work that can be explored. Further configuration and data collection with the system can enable Bayesian-based a posteriori detection and classification of a larger set of malicious and non-malicious signals. Further integrating our system with a configurable open source 5G network can enable network function protocol vulnerability assessment. Lastly, outdoor experimentation with traffic from many users in distributed geographic areas can improve the robustness and applicability of the MCS optimization model through collection of higher variability data. Deploying our system in outdoor environments with a large-scale number of devices and users can help enable zero-trust networking. Thank you for listening.
Okay, so thank you. Now we are open to questions. There is Francesco. Please go ahead.
Yes, thank you for the presentation, for the very nice work. I have a question about the feature selection process. I've seen that you have several features inside to give an input to your algorithms. I wonder how you selected those features, if it's only based on experience because they are well-known features, or if there is a sort of automated process to distill the features.
Thanks for the question. That's a really great question. So for feature selection, as we mentioned, there are two ways when we're selecting, two approaches when we're selecting the features. The first one is based on the experience, like for example, the signal noise ratio, the throughput, the CQI that reported by you. These are like important indicators when regarding the performance, whether there is a jamming or not. So these are selected based on the feature, the characteristic of the feature itself. And another way is that we when we do the like doing the model, we also evaluate what's the weight of each of the feature and use the automatic feature selection when we select it, because we collect a huge number of the data, and so these are the ones that we finally selected, so we can reduce the data required to tune the parameters.
Okay, thanks.
Thank you.
I have a question. As far as I understand, you generate different jamming interference profiles, right?
Yes.
I was wondering how many of these samples you need to have until your model is trained.
That's a good question. So we didn't indicate it in the presentation, but we put it in the paper. So one requirement or one target that we're doing is we want to use this in real time. So the collection time, like for the model to make a decision of it, is based on the experiment is less than 0.8 seconds. And then regarding the collected data, we also we want like when we use it in a different scenario on the IoT devices or using transfer learning, we want to make sure that it doesn't require a very long time of the training data in order to be able to train the model. So so we are collecting the samples that we use to train the current model is about 24,000 samples of the data, but we are collecting in a very like about 100 milliseconds per sample. Like the intervals between the two samples are less than 100 milliseconds. So these are used for training, and then for the decision point, we're using temporal-based learning. So we used 8 milliseconds of the data to make the accurate decision.
Okay, thank you.
Thank you.
Okay, so if there are no other questions, we'll move to the third presentation made by Yerlas from CNAM, France. Oh,
hi, everyone. Yes, I'm here.
Hi.
everyone, and welcome to my presentation. The main purpose of this speech is to show how we can reach a complexity performance trade-off while using a robust access point clustering in edge computing. This presentation is organized as follows. First, I would like to introduce the context and the motivations of this work. Second, I will present some of the key concepts on which our work is relying on. Then I will be presenting our major contribution. And finally, I will expose performance evaluation of the proposed approach. So according to GSMA report of 2020, by the end of 2019, half of the world population were using mobile internet. So these numbers are supposed to increase significantly in the coming years, what will cause huge resource consumption, hence a reduction of end users' quality of experience, especially with the emergence of the 5G new services, such as URLLC and eMBB that require a very low latency and very high bandwidth. So to cope with these new requirements, mobile network infrastructure is evolving continuously. First, at the RAN level, where the traditional RAN has evolved to Cloud RAN and then to virtualized RAN in order to be able to deploy a larger number of base stations. Second, at the core level, such as the virtualization of core functions and also the separation of the control and data plane. And we also have the integration of the MEC technology, which is recognized as a 5G key enabler. Well, it allows moving computing and storage capacities to the edge to help to meet the requirements of pervasive applications. For the background, well, in this part, I will present a set of concepts on which rely our work. So we have the first concept is the evolution of the RAN, where BBU's functions are disaggregated into two units, CUs and DUs. And we have, when combining the MEC and the VRAN technologies, this yields several challenges, and one of them is how we could efficiently decide on which MEC server a CU will be installed. The other concept is the data analytics. So how could we make use of the data analytics to optimize MEC orchestration problems? In figure 1, here we have a representation of the reference MEC infrastructure. So we can see that the MEC servers are installed between the base stations and the core network. So this installation depends on the network operator needs. And we can also see that the MEC server can host not only the virtualized functions from the RAN and the core networks, but also the virtualized application servers and the network services. So our contribution consists of proposing a robust clustering model of access points performed at the pre-processing phase, and then trying to find an optimal pattern to assign these clusters to the available MEC host installed at the edge. So we need to take into consideration the infrastructure capacity constraint, the traffic demand fluctuation, and the coherence of the assignment plan. And finally, we will evaluate our work using a real-world dataset. So for the spatial clustering, it consists of grouping together access points that generate the same traffic demand behavior. And here we have the mathematical formulation. So as the objective function, we need to minimize the gap between the maximum and the minimum access point demand. Within each cluster, we have a set of constraints, like the capacity constraint. And for the variable, we have XYC. It's equal to 1 if the access point I belongs to cluster C. For the orchestration algorithm, the objective is to schedule the assignment of clusters to the set of available MEC hosts for each time slot and during a period of 1 week. We can distinguish two types of operations. So we have the assignment operation and the switching operation. And we have extended the orchestration model from literature to fit with the spatial clustering decision. To have the same orchestration decision applied on access points of the same belonging to the same cluster. For the mathematical formulation, we can see here as the objective function that we aim at minimizing the both both the assignments and switching costs that are directly related to the distances between access points and the MAC host. We have also a set of constraints to respect, such as the capacity constraints and the coherence of the assignments and switching plans constraints. So for the simulation scenario, to evaluate our proposal, we have used two different datasets collected at two different regions in France, Paris and Lyon, and we have used different infrastructure sizes, and data was collected as the French mobile operator as part of the Cancan project. Here we have the four algorithms that we've been using. So MEC-A is the reference orchestration model without spatial clustering. MEC-ACS is our proposal. MEC-ACG is the reference orchestration model without spatial clustering and using dynamic variable generation approach for the resolution. And for MEC-ACG, CS is just as MEC-ACG but using spatial clustering per computation. So we assess the results through CDF of spatial and time complexity metrics that are execution time and maximum memory consumption. We also added the assignments and switching cost and the achieved optimality gap percentage. So we are going to begin with the Paris dataset. We have for the optimality gap, we reached the 0% by all the approaches except for MEC-A when using 50 MEC facilities, because it has stopped before getting any result because it has a very big memory consumption. And here we have the memory usage in figure A and B. So when using 20 MEC hosts, so MEC-ACS has a constant maximum memory usage through all locations, and it represents the lowest values, followed by MEC-ACG and MEC-ACG-CS. Meanwhile, MEC-A is the most memory consuming. For 50 MEC hosts, we have MEC-ACS and MEC-ACG have a very close memory consumption on average, and on the other side, MEC-ACG-CS has the highest consumption, reaching 19.4 gigabytes. For the execution time, so in figures A and B, so we can see that when using 20 MEC hosts, MEC-ACS is the fastest approach, followed by MEC-ACG. And on the other side, when increasing the infrastructure size to 50 MEC hosts, MEC-ACG becomes the fastest one, followed by MEC-ACS. For MEC-A and MEC-ACG-CS, they need a higher time, where MEC-ACG-CS represent the highest one. And here it is worth mentioning that in existing work, it has been stated that using 20 MEC hosts should be sufficient for scope as the Parisian one, even with a strict latency and bandwidth requirement. For the assignment cost, we can notice that the approaches without the spatial clustering yield lower assignment cost. In fact, the spatial clustering adds constraint to the orchestration problem that should produce the same assignment plan for all access points that belong to the same cluster. Here for the switching cost, so we can also see that the spatial clustering adds an additional switching cost. We also can see that when we increase the number of MEC hosts, this reduced both the switching and the assignment cost for all the approaches. Now we are going to talk about Lyon dataset. So we are going to begin with the optimality gap, where we have reached the 0% when using MEC-ACS, MEC-A, MEC-ACG, and with 10 and 20 MEC hosts. So we can also notice that we have reached the 0% optimality gap when using 30 facility only with the MEC-ACS, and for MEC-A we couldn't reach any result when using 30 MEC facilities. For the memory usage, so from figure A, B, and C, we can notice that the best case always corresponds to MEC-ACS with a constant memory consumption, followed by MEC-ACG. And MEC-A has the highest memory consumption peaks for both cases, 10 and 20. And meanwhile, MEC-ACG-CS has an intermediate consumption between MEC-ACG and MAC-A. For the execution time, we can notice that MAC-ACS is the fastest approach here in blue. And for all the cardinalities, on the other side, MAC-ACGCS gives the worst case. This can be explained by the fact that we are using large scales, so we aggregate the demands of access points that belong to the same cluster to get the cluster demand. For the assignment cost, we notice here that approaches using spatial clustering model are higher than cost generated by the approaches spatial clustering free. So we also can see that the assignment cost decreases when we broaden the MAC infrastructure size from 10 to 20 and from 20 to 30. For the switching cost, we can see also that when applying the spatial clustering model, we generate an additional switching cost. And also when using 30 MAC host here, so we can see that MAC-ACS and MAC-ACG have the same switching cost for some instances. Now I would like to summarize the obtained results in the following point. For MAC-ACS, we can see that our spatial clustering helped reduce time and space complexity. And also when we increase the number of MAC hosts, for the most of the time, it reduces cost, but increased time and spatial complexity on the other side. And due to its high memory consumption, we could not execute the MAC-A case for the two highest MAC infrastructure sizes that are 50 and 30 for Paris and Lyon dataset. And finally, our goal is to find a trade-off between time, space complexity, and cost. So, to sum up, we have proposed a spatial clustering model that regroups together access points revealing the same spatio-temporal traffic behavior through time. We have integrated into an orchestration problem to help increasing its robustness. Results from extensive simulation on real-world dataset have shown that our proposal helps reducing time and space complexity compared to other solutions from literature, especially for small to medium instances. And finally, our framework can be carried out in a real-time manner, even if it entails additional cost. And in perspective, we intend to put more requirements on execution time for real-time MAC orchestration while integrating real-time traffic prediction. Thank you so much, and please feel free to ask questions.
Okay, thank you. So now we are open to questions.
Actually, I could not share.
There is Francesco. A question. Please go ahead, Francesco.
Yes, thanks for the presentation and for the nice work. I was wondering, is there, you considered two data sets, two scenarios, no? Paris and Lyon, if I remember correctly.
Yes.
Okay. So, apart from the results that you have obtained, what are the main differences between these two cases in the scenario? So the results, you have shown that they provide different messages, but did you expect by knowing the difference in the input that you would have a different behavior also in the output?
Yes, actually what we've been doing is that we applied the same orchestration method or framework on two different datasets. So for Paris dataset, actually the Paris, the city of Paris, it is known for being crowded and there. For example, we wanted to test on two different cities. For Paris, we have different traffic demands compared to the other cities. For example, we have another difference in terms of the number of base stations or the access point. for Leon dataset, we have 300 base stations, and for Paris we have taken like 500 base stations. So the main difference is in the traffic demands.
Is it also in the density of the? I mean, the
Yes.
Traffic
Yes.
per kilometer, traffic per base station?
Yes, exactly, because for Paris, it is known for being a very dense area compared to Lyon dataset.
Okay, okay. Thank you.
Thank you.
Question from the general chair?
No, actually, we don't have any question, but I just want to congratulate for a good presentation.
Thank you.
Okay, so that if there are no other questions, I will move to the last presentation. Okay. In the meantime, I'm going to ask to Carol Basil to raise the hand, and I'm going to start sharing here.
Just a moment.
Yes.
Sebastian. So no, we have an issue here because I think that nobody is here to present this paper. Is anybody in the between the attendees going to answer questions for this paper? I don't see any author of this paper connected.
Yeah, you're right. I don't see neither Carol or Joanna.
So in principle, this is should be regarded as a no-show. And now I think we have two options, and I submit this to our steering committee chair, if he is online. I think yes, Prosper.
He is.
Okay. So we can either play the video because they send us the video or not. It depends on you, basically. But it's clear that if there is nobody here to answer questions, this paper will not be included in IEEE Explore.
Yeah,
I think.
you're right. Just my question is that have they been made aware that they had to be online?
Well, I think this was clear since the beginning.
No, yeah, it was, yes. So I think there is another possibility that sending an email and let's say give a chance, we can play the video and give them a chance to join during the video.
I have already sent them an email just during the previous speaker, but nobody replied.
Nobody replied, so we don't know. So I would suggest to play the video, and to wait for them a message explaining why they didn't attend. If there is a good reason, that's okay. If there is no good reason, it should be probably removed from the documents, from the package sent to IEEE Explore, because this is a rule for everyone.
Yes, of course.
But it depends. They may have a good reason. I don't know. I don't want to state. But let's play I would suggest to play the video.
Okay, so Sebastian, please go on.
Yeah.
Thank you.
Thank you.
Carol Basil, and I will be presenting our work on the dissemination of cyber threat intelligence through Hyperledger. Cybersecurity companies are relying on blockchain technology to provide security solutions due to several advantages it brings. We use DLTs to share cyber threat intelligence, which provides new means for SOC teams to disseminate securely threat data. In this presentation, we will be presenting a blockchain model to securely disseminating CTI between parties using Hyperledger. Shared CTI data will be visualized using a customized schema to simplify human analysis tasks. In the first section, we provide a brief description about CTI. The second, an overview of blockchain technology. We present our implementation and describes our contribution. In the third section, we conclude by outlining our future work.
Sebastian, are you sure you have activated the...
Yes, I'm sure, but the video is going...
Cyber threat intelligence aims to detect, respond, and prevent potential cybersecurity incidents by understanding the threats that might target an organization, and thus reducing the attack surface to mitigate harms and protect the system. Before identifying the key concepts that underpin cyber threat intelligence, it's worth to identify nuances in the terms of data, information, and intelligence. Data is considered as unrefined and unfiltered information in the form of symbols and signals collected from the operational environment. Once this data is processed and refined, it produces information. The intelligence is when the obtained information is then analyzed and transformed to a format that can be used by various tools such as automation and analytics to take operational action such as detection, prevention, and response. The intelligence cycle is made of 5 phases. The first one, identify intelligence gaps and prioritize them to define the strategy and objectives of a CTI function. Phase 2 determines which data source is needed and how to get it. Phase 3 correlates and validates the data into useful information for analysis. Phase 4 create actionable intelligence from information processed in the previous phase. Phase 5 distributes and packages intelligence products to the customer.
I think the video has some issues.
It seems to be
because
secured by a blockchain algorithm for the speech.
Because the video is going on.
Consumer of the intelligence and the aim behind it helps to identify 4 categories of threat intelligence. Strategic, which is a high-level information that shows the big picture of past, present, and future trends in the threat landscape. Operational, which is a specific information about the nature and purpose of the incidents and the attackers. Tactical refers to the tactics, techniques, and procedure of the attackers. Technical, which is information such as technical indicators that about malware and campaigns. This section overviews the blockchain technology, presents a comparative of several DLTs, and depicts the advantages of using Hyperledger Fabric for threat intelligence sharing. Blockchain is a distributed ledger containing digital events or transactions which have been shared between participating parties in public or closed networks. Blockchain assure a decentralized network where each transaction is validated by consensus of the majority of the participants in that ledger. The block of chains is a growing list of records linked using cryptography and hashes. Each block contains a cryptographic hash of the previous block, a timestamp, and transaction data which contains the payload. The peers in a network will validate each transaction using cryptographic algorithm and verify it. After verification, a block is formed containing the payload, a header that is the hash of the previous block and its own hash. The block is then added to the existing blockchain to form the blockchain networks. Blockchain has many important security properties that give it a benefit versus any traditional data sharing technology. Notably, it's a secure network, ensuring anonymity. It's a decentralized solution, providing an integrity checks by design. This table compares multiple blockchain platforms, mainly Bitcoin, Ethereum, Hyperledger, Ripple, and Cadena, in terms of multiple parameters such as application, performance, governance, contracts, consensus, type, if it's private or public, permissioned or permissionless network, if the transaction data are encrypted or no. Based on this table, we can consider that the Hyperledger is the most suitable one to be used for sharing CTI. Hyperledger Fabric is a permission DLT providing a general purpose framework that allows a variety of applications due to its access control features. Below, we define what is a peer, what is a node, what is an orderer, and what the role of a certificate authority.
And the video has really several issues because I guess the audio is not synchronized with the slides.
Yeah, video's issues and authors are not.
Yeah, this is what I'm writing to the authors right now. That the video is not synchronized and they are not present.
And they're not answering emails as well.
Yeah. Maybe at this stage, I think we should stop the video. I think it's useless. We cannot follow the paper anyway. I think that you cannot you cannot take the responsibility of this.
Hello? Hello?
Yes, we
You hear me?
Yes.
Okay, so additionally, we had also blackout here. Tecnico di Milano, connected by our phones. This is on the top. It's really on the top. So I think that
What is the topic of the conference?
Sorry?
What is the topic of the conference?
Reliability.
Oh,
Indeed, Prosper, I am at home with the secondary connection, and so I was telling Guido that I can take the lead of the hosting if needed. So, but I think we are at the last paper of the session.
So while we are.
Yes, it was the last one.
So Sebastian is joining me.
Oh, I thought it was...
So while we are waiting for the, I think we can take a break before going to the gather.town session. We hope that we will be able to connect again. But in any case, let's say that we can, so this session is closed. We can rejoin, let's say at 4:05 or 4:10 for the gather.town session. So I sent you the links. I can share also my video with my screen with the instructions. This is also the participation link. I think you can see it. And so let's say that we will start the gather.town session towards 4:05. Okay. So again, thank you very much for attending. And also, thank you for all the speakers of this session. And if I think Gino, I don't know if he's still connected. Thank you, Gino, for your very interesting talk. And sorry for this multiple technical problems. Okay. So see you in a quarter of hour, 20 minutes. Bye.
Gather down DRCN.